Welcome my dear learners for this course on tribology. From today we are beginning a new topic, that is hydrodynamic bearings. Let us discuss hydrodynamic bearings in today's lecture. The hydrodynamic bearings are one in which the fluid film pressure is produced only because of rotation of journal inside the bearing. The journal takes a position such a way that the rotation of journal is sufficient to produce fluid film lubrication, and there will be a change in pressure which will produce a force that is enough to withstand the load acting on the journal. In case of hydrodynamic bearing, we are not using any external accessories to support the journal inside the bearing. The rotation of journal itself will produce the fluid film lubrication, and also the change in pressure is sufficient to produce a force that can withstand the load acting on the journal. What I mean to say is that we have a journal which is nothing but a shaft like this, which is rotating inside a bearing, right? So bearings are the devices, mechanical device which will support and withstand the load. So bearing is supporting the shaft will be rotating. The rotation of the shaft itself will produce the continuous circulation of lubrication or fluid film, and also the change in pressure takes place which will produce a force that can be sufficient to withstand the load acting on this shaft. We won't mount a shaft in a bearing without mounting anything on the shaft. The shafts are used for power transmission. We'll mount gears or pulleys on these shafts. The load acting on the shaft will be supported by the bearing. How it will be supported? It will be supported by the change in pressure that will produce as a counter-attacking force that can withstand the load acting on this shaft. So we are not using any external accessories to generate the pressure which will produce as a force to withstand the external acting load on the shaft. The shaft is nothing but journal. Journal is a rotating element of the bearing. So journal and bearing, this is an example of hydrodynamic bearing. Now how does this pressure development mechanism takes place in an hydrodynamic bearing is a topic of interest. Apart from that, if the rotation of the journal is very high, let us say the journal rotates at very high speed, and the viscosity of the lubricant present between the bearing and the journal is very high, and the load acting on this journal is very small, then both the journal and the bearing will be concentric. That is, the shaft runs concentrically with the bearing if and only if the load acting on the shaft is very small and the speed of the journal is very high and the viscosity of the lubricant is also very high. That is, the journal rotates concentrically. The journal rotates concentrically inside this bearing. So this is journal, right? So journal is nothing but shaft. So this journal rotates concentrically if and only if the load acting on this journal is very small, the speed of the journal is very high, let us say infinity, and the viscosity of the lubricant present between the journal and the bearing is very high. So the hydrodynamic bearings in which the load acting on the journal is very small, the speed of the journal is very high, and the viscosity of the lubricant is very high, and the eccentricity produced between the journal and bearing can be neglected. Such bearings are termed as lightly loaded bearings. What you call for that? Such bearings are called as lightly loaded bearings. Lightly loaded bearings. So for lightly loaded bearings, the load acting on the journal is very small, second thing is that the speed of the journal is very high, speed of the journal is very high and the viscosity of the oil lubricant oil is sufficiently high. If these three cases are satisfied, then the eccentricity of the journal can be neglected. That is, the eccentricity is very small. The eccentricity is very small. So such analysis is termed as lightly loaded bearing analysis, which is done by using Petrov's equation. This analysis of lightly loaded bearings, that is the expression for coefficient of friction for lightly loaded bearing given by a scientist by name Petroff, has been explained in another lecture given by me. So kindly click on the link given in the description below to get access to the lecture where I have derived Petrov's equation. So Petrov's equation for lightly loaded bearing is a very important concept for examination point of view, and also to analyze problems or numerical problems on lightly loaded bearings, wherein which I have derived the expression for coefficient of friction for lightly loaded bearing. So kindly click on the link given in the description to get access to the lecture on Petrov's equation and go through it. Moving ahead, let us discuss how this pressure development takes place in the hydrodynamic bearings. So next concept is pressure development mechanism. Let us discuss pressure development mechanism. Since I already derived lecture on Petrov's equation, I don't want to repeat it once again. Let me skip that and let us move on to pressure development mechanism. As I said, in case of hydrodynamic bearings, the fluid film pressure is developed just by the rotation of the journal itself. We are not using any external devices to generate the fluid film pressure. And journal takes a place such that the rotation of the journal will cause continuous circulation of the lubricant, and also the change in pressure that can produce a sufficient enough force to withstand the load acting on the journal. How does that pressure development takes place in an hydrodynamic bearing is the next topic. Now let us consider one surface is fixed and another surface is moving, which is nothing but a simple Couette flow. This year people already learnt in our UG course on fluid mechanics, Couette flow. That is, one surface is fixed and another surface is moving with a velocity u. So if I draw in velocity profile for one surface is fixed and another surface is moving with a velocity u, I will get a linear profile like this. The velocity is maximum at the top surface and velocity is 0 at the bottom surface, because the bottom surface is fixed, right? So here also I will get the same profile, correct? If I draw a velocity profile, it will be linear for Couette flow, where one surface is fixed and another surface will be moving with a velocity u. Let us take the distance as h, this as AB, this as A dash, B dash. Now if you carefully observe, at any point on this fluid film between the two surfaces, that is one surface is fixed and top surface is moving with a velocity u, if I take a pressure at any point, the pressure remains constant. The flow is happening only because of the top plate or top surface is moving. Such flows are termed as velocity induced flow. If I want to explain velocity induced flow in taking a real life example, let us consider a flowing river. If I throw a negligible mass plate onto the river, the plate will also flow along with the river. This is because of the reason the layer adjacent to the massless or the negligible mass plate is moving with some velocity. So therefore the plate will also move with the river. So this is purely because of velocity induced flow. So this is velocity induced flow in which the pressure is constant. Let us take pressure P0 at exit and Pi at inlet. If I observe in a quiet flow or velocity induced flow, this is what velocity induced flow. The pressure is constant. Clear? Another case is flow between two stationary parallel plates. Let us take case 2 as flow between two stationary parallel plates. Consider two stationary parallel plates like this. Let us take the entrance as A dash and exit as B dash. The flow between two parallel stationary plates is nothing but Poisson flow. This is also you have learnt in your UG course on fluid mechanics. Poisson flow is because of pressure difference. This is pressure induced flow. Pressure induced flow. Now let us consider the distance between these two plates as h, and these two plates are stationary. Now if the movement of A dash B dash takes place perpendicular to AB, that is in the vertical direction, if I press this, then whatever fluid present inside between these two plates will squeeze us out. Correct? Let us say I have some amount of fluid inside these two stationary parallel plates. This is both are fixed. Now if I press this downwards in the vertical direction, the fluid or the oil or the lubricant will squeeze us out like this. So thereby the pressure difference will be created and flow will be induced. And we all know that the velocity profile for this is parabolic in nature, wherein which the velocity is 0 at lower plate and the velocity is 0 at top plate, and the velocity is maximum at the center, and the velocity profile is parabolic for Poisson flow. So if I draw a velocity profile, it will be like this. If I squeeze us out at the center, if I press it, the flow will be takes place outward, and the flow takes place if and only if we have pressure difference, right? So therefore let us take the section as C dash. So here let me have a maximum pressure, and the pressure decreases and reaches 0 at both extremes, that is A dash and B dash. Whereas in case of Poisson flow or pressure induced flow, due to pressure difference between the inlet and exit like this, due to the pressure difference at inlet and exit, let us take this as Pi and this as P0, wherein which Pi is greater than P0. So lubricant always flows from higher pressure region to lower pressure region, and the profile will be like this. So this is an example for Poisson flow. Correct? Velocity profile will be parabolic and velocity will be maximum at the center. This you people already learnt in our UG course on fluid mechanics. This is quiet flow or velocity induced flow. This is pressure induced flow or Poisson flow. How I can develop how I can induced flow because of pressure difference, that is by squeezing the top surface in the direction perpendicular to the bottom surface, thereby the lubricant which are present between these two plates will squeeze us out like this, and the flow will happen if I have maximum pressure at the center and minimum pressure at the extreme ends. So thereby the flow takes place from C dash to A dash and C dash to B dash. So this is a second way, that is velocity induced flow and pressure induced flow. But in case of bearings, the pressure development takes place because of converging section. So the topic of interest is not these two. The very important topic is how does pressure development takes place in a converging wedge. So pressure development in converging wedge. So this is what we should understand properly. Pressure development in converging wedge. Let us consider a top surface moving with a velocity u, and let us have a converging wedge like this. Which is fixed. This wedge is fixed. Let us take the converging section in the direction of flow like this. Let us take this as A dash and B dash. The top plate or the top surface is moving with velocity u. Let me take B dash like this. The fluid enters this section from A dash and leaves from section B dash. Now initially let us consider the profile to be linear like this. Profile to be linear like this. Linear like this. Now the fluid is entering with a velocity u. Let us take the velocity as u initial. Let us take this as this height as hi and this height as h naught. So this is the initial case I am taking for analysis. Since one end is fixed and another end is free, the average velocity can be taken as u by 2. That u by 2 will be the average velocity. So therefore, what is the volume flow rate? What will be the volume flow rate? The volume flow rate is nothing but velocity times the area. Let us take the width as unity, that is the length perpendicular to this board can be taken as unity. If I take the length perpendicular to the board as unity, then the cross sectional area will be hi into 1, that is hi. The average velocity is ui by 2. So therefore, the average velocity will be ui by 2 and the flow rate is given by ui by 2 into hi. Correct? So this is the initial flow rate of the lubricant entering the section A dash. Once the lubricant enters the section A dash, since the fluid is incompressible, the oil is incompressible, if you observe, the volume flow rate should remain constant. But will it remain constant? No, right? Because it is moving with a velocity ui, but hi is not equal to h naught. hi is not equal to h naught. H naught is reducing, because of which the velocity profile, which is linear, will be distorted. This will be distorted and will become concave. So since h naught is less than hi and the fluid is incompressible, but for us the flow rate should remain constant for an incompressible fluid, that is volume flow rate should remain constant. Since the volume flow rate should remain constant, the velocity profile will get distorted, because of which the pressure difference will be created. So because of this, velocity profile will be distorted. Velocity profile will be distorted and the pressure difference will be created. So here I will get a concave profile and here I will get a convex profile. That is, if I draw the profile, what I will get, the profile will look like this. Let me erase this one. I will get a profile like this. So this is moving with a velocity u and I will end up with a distorted profile like this. So this is the converging wedge, what I considered. This wedge is fixed like this, and here convex because velocity will boost up. So what is happening? So because of h0 is less than hi or hi is greater than h0, the velocity profile will be distorted. It will be concave here. It will be concave and it will be, the pressure will be boosts up, so therefore it will become convex here. So the velocity profile is no more linear. The velocity profile will be concave at entry, that is at A dash. So since pressure boosts up, it will become convex at exit, that is at B dash. So thereby the pressure development will takes place. So this is what happens in case of hydrodynamic bearings. That is, if I want to explain, initially let us consider at the beginning we have a bearing inside which we have a journal at rest. So this is the center, let me take. This is center, let me take. Then what happens? It starts rotating. Then if I consider, after some moment it will rotate and come somewhat stands here with certain gap. Let the center come somewhere here and it is rotating clockwise. If you observe, so if I take half of which, so if you observe the section above this one, let us take the section as AB, section above AB. How it is section above AB? It is converging section. Area is decreasing in the direction of rotation, correct? In the direction of rotation, the area is decreasing. This somewhat like converging section, right? Below AB, it is diverging section. In the diverging section, it works with negative pressure gradient. In the converging section, it works with positive pressure gradient. Thereby, the pressure development takes place and the journal moves towards the center like this, and finally it will coincide or runs concentrically if it is lightly loaded like this it will be, and finally it will run concentrically with the bearing if it is lightly loaded and the speed of the journal is very high and the viscosity of the lubricant is very high. So this is how the pressure development takes place in hydrodynamic bearing. So this is the explanation for pressure development mechanism in a converging wedge or converging cross section. Now let us move ahead and discuss Reynolds equation in 2 dimension, which is the most important topic of hydrodynamic bearing. Come, let us derive an expression for Reynolds equation in 2 dimension. Next, moving ahead to derive Reynolds equation in 2 dimension. Moving ahead to derive Reynolds equation in 2 dimension. Now to derive Reynolds equation in 2 dimension, let us consider the pressure development mechanism in a converging wedge, which I explained just now. So if I consider the same case, we have the top surface moving with velocity maximum, let us take it as capital U, and we have a converging wedge like this. We have a converging wedge like this. And this wedge is fixed. Let us take this as fixed edge. And we have height h, I, and this as height h naught. Let us take an element here, somewhere in between. Let us take an element for analysis. Let me consider an element somewhere here like this. For this element, if I consider, let us take this as height h. Let me measure y in this direction, y, and this I take it as h for the element. Now pick up this small element and analyze. If I pick this small element for analysis, I can take the element, the cubical element like this. So I took this element here. Now if you observe, at the entry we have higher pressure, at the exit we have lower pressure. Due to the pressure difference, the flow happens. So here we have pressure as high, so therefore force is pressure times the area, right? Let me take this length as dx, this length as dx, and this length as dy, and this length as dz. So I have taken the elemental volume dx, dy, dz. So here I have pressure P acting over area. This length is how much? Dy. This length is dz. So therefore here I will have force as P times dy dz. So here I will be having an pressure as what? There will be change in pressure. So you know how to represent change in pressure, that is P plus dou P by dou x dx. So this area will be dz dy, right? That is dy dz. So I have plotted the forces acting along x direction. Now since the plate is moving with velocity u like this, on the top surface the shear force will act opposite to the velocity. So since the plate tries to move this element from left to right, the resistance will be from right to left, correct? So therefore here I have the shear, here I have the shear force. So what will be the shear force? Shear stress times the area, correct? So how much is the shear stress? Let us take the shear stress as tau. And what is the area? So this length is dx and this length is dz. So it is dx dz. So since here it is acting from right to left, here it will be from left to right. So there will be a change in stress. So that will be how much? Tau plus dou tau by dou y dy. So this is on y plane times This length is how much? Dx. This is dz. It is dx dz. Right? Now this Reynolds equation in 2 dimension is derived based on many assumptions. Those assumptions are also very important for us. So the assumptions are, the first assumption is that the inertia force of the oil is neglected. The inertia force of the flowing oil is neglected. Inertia force of the oil is neglected. Second thing, the oil is Newtonian. What do you mean by the oil is Newtonian fluid? It obeys Newton's law of viscosity. That is, the shear stress is directly proportional to rate of shear strain. The oil is Newtonian fluid. That is, it obeys Newton's law of viscosity. The oil is Newtonian fluid. The oil is Newtonian fluid. Next, the viscosity of the oil is constant. The viscosity of the oil is constant. Or lubricant is constant. Next, there is no slip between the lubricant and the bearing. So this is the bearing. So here we have lubricant. There is no slip between the bearing and the lubricant, which means that at the boundaries, the velocity, if the velocity is u at the top face, then the velocity of the fluid film adhere to this surface is also u. There is no slip between the bearing surface and the oil. This is journal and this is bearing. So here also there is no slip. At y is equal to h, at y, this y is equal to h at this surface, there is no slip. Therefore, the velocity of the fluid film adhering to the bottom surface will be 0. The velocity of the fluid film adhering to the top surface will be u. This is based on the assumption that there is no slip between the lubricant oil and the bearing surface. So therefore, next assumption is that no slip occurs between oil or lubricant and the bearing surface. Next assumption is that the oil is considered to be incompressible, which means that the volume flow rate is constant. That is, the lubricant oil is incompressible. How, sir? How the volume flow rate is constant? Because volume flow rate is defined as velocity times the area. Here the area is high, here the area is small. Correct? Here the area is high, here the area is small. Since it is converging section, here the velocity will be low, here the velocity will be high. This is somewhat similar to nozzle, right? So it's somewhat similar to nozzle. So here the velocity is low, here velocity is high. So ui by 2 hi should be equal to u0 by 2 h0, where u0 is greater than ui. So thereby the volume flow rate will remain constant. The oil is incompressible, which is nothing but conservation law of mass. The mass flow rate should remain constant. How much lubricant enters, that much lubricant should come out. If I measure per second, it should remain constant. That is what mass flow rate, kg per second. Here I am measuring volume flow rate, meter cube per second. And also our next assumption is that there is no flow in the direction perpendicular to motion. So this is the direction of flow, and there is no flow in the direction perpendicular to motion. That is, there is no end leakage. There is no flow in the direction perpendicular to motion. Means what? No end leakage. So based on these assumptions, we can derive Reynolds equation in 2 dimensions. Let us pick one by one, incorporate these assumptions and derive Reynolds equation in 2 dimensions. What does the first one says? Inertia force of the oil is neglected means what? There is no acceleration in the oil. So if I pick up the first assumption, there is no acceleration in the oil, so therefore sum of forces must be equal to 0. Sum of forces must be equal to 0. So what are the forces acting on this elemental length? Let us take the force in the direction positive x-axis as positive, negative x-axis as negative. So therefore from the equilibrium of forces we have P times dy dz minus of P plus dou P by dou x dx dy dz minus tau dy dz plus of tau plus dou tau by dou y dy dx dz. Here it is dx dz, sorry. This must be equal to 0. Right. So now if I simplify what I will get? I will end up with P dy dz minus P dy dz minus dou P by dou x dx dy dz minus tau dx dz plus tau dx dz plus dou tau by dou y dx dy dz must be equal to 0. So here these two will get cancelled and these two will get cancelled. I left out with dou P by dou x dx dy dz is equal to dou tau by dou y dx dy dz. So these two will get cancelled. Correct? Here I have negative sign. I will take this term to right hand side. So if I take this term to right hand side, these two will become equal. So I cancel off the volume. So hence our first assumption, it is inertia force of the oil is neglected, which is nothing but sum of forces is equal to 0, will yields us dou P by dou x is equal to dou tau by dou y. Next, move for the second assumption. The oil is Newtonian fluid. What do you mean by this? The oil obeys Newton's law of viscosity. What does Newton's law of viscosity states that? Newton's law of viscosity states that shear stress is directly proportional to rate of shear strain. That is, from our second assumption we have shear stress is equal to absolute viscosity times dou u by dou y. Correct? This is from Newton's law of viscosity. So therefore put it here. Based on our second assumption, I recollected the Newton's law of viscosity. So therefore replace tau by viscosity times rate of shear strain. So therefore I will get dou P by dou x is equal to dou by dou y times eta dou u by dou y. Right. So if I simplify, what I will get? So incorporate the third assumption also. What is our third assumption? The viscosity of the oil is constant. So since eta is constant, I can take eta outside. Correct? I can take eta outside because viscosity of the oil is constant. So eta is constant. I will take it out, and if I send it here, I will end up with dou square u by dou y square. I will take it out and send it here. It will become 1 by eta dou P by dou x. 1 by eta dou P by dou x. Right? So this is what I got. Now if you carefully observe, U varies only in the direction of y and pressure varies only in the direction of x. U does not vary in the direction of x because U is constant. It varies with maxima, it is 0 at bottom. So U varies only in y direction and pressure varies only in x direction. So pressure is maximum here, pressure is minimum here, velocity is maximum here, velocity is minimum here. So velocity varies in y direction, pressure varies in x direction. So therefore I can write it as normal derivative rather than using partial derivative, right? So partial derivative is employed if and only if U is function of more than one direction. If U is a function of x and y, then I should use partial derivative. Here U varies only in y direction, whereas pressure varies only in x direction. At the inlet it is high, at the exit it is low. So therefore I can write this as d square U by dy square is equal to 1 by eta dp by dx, right? Now let me integrate that expression. What I will get if I integrate that? How many assumptions we have employed? We employed 3 assumptions. Move for the third assumption. Third assumption will give us boundary condition. First let us integrate this equation. Let us take this as equation number 1 and take this as equation number 2. Now integrate equation 2. So if I integrate equation 2, what I am going to get if I integrate equation 2? Integrating equation 2, if I integrate equation 2, I will get du by dy, integrating with respect to dy, I will get du by dy is equal to 1 by eta dp by dx dy. Since we don't have limit, it is indefinite integral, therefore I should have constant of integration. Now again if I integrate, integrating, what I will get? If I integrate again, I will get u is equal to 1 by eta dp by dx. So integrate with reference to y, I will get it as integration of dy is what? Y only, right? Integrating with respect to dy, integral of dy is y. Now again if I integrate with reference to y, I will get y square by 2 plus c1 into y plus c2, constant of integration. So I got the equation for this one like this. U is equal to 1 by eta dp by dx y square by 2 plus c1y plus c2. Now use the next assumption, that is no slip occurs between oil and the bearing surface. So if I recall this assumption, no slip occurs between the oil and bearing surface, what will be the boundary condition? What will be the boundary condition from this assumption? What will be the boundary condition? Since there is no slip, at y is equal to 0, velocity is maximum. At y is equal to h, velocity is 0. Since there is no slip, right? So what is the boundary condition? At y is equal to 0, velocity will be maximum, capital U. At y is equal to h, velocity will be 0. Right, so if I substitute and solve, what I will get? So from first boundary condition, velocity will be capital U, put y is equal to 0. So first boundary condition will yield us y is equal to 0, these two terms will get cancelled, C2 will be capital U. C2 will be capital U. Now use second boundary condition. If I use second boundary condition, what I am going to get? If I use second boundary condition, first you substitute this here. So this will reduce us to U is equal to 1 by eta dp by dx y square by 2 plus C1y. C2 is capital U, that is maximum velocity. Now put second boundary condition. If I put second boundary condition, I should substitute y is equal to h and small u is equal to 0. So if I do that, 0 is equal to 1 by eta dp by dx, this is h square by 2 plus C1h plus u. So hence C1 will become minus of capital U by h minus, so minus are taken out, it will become plus 1 by 2 eta dp by dx into h, correct? Minus u by h minus h square by h is h, correct? So now substitute C1 to this equation. So hence, therefore, what is the equation for velocity you will get? So velocity u is equal to 1 by 2 eta dp by dx C1 will be y square minus h into y, because we have y term here, so it will become h into y. It will be hy, right? Y square minus 1 by 2 eta dp by dx hy, y square minus hy. So I will get y square minus hy. Y square minus hy minus, I will take u common. So C2 is also u, here also I will have u. So I will take u common. So if I take u common, that is capital U, maximum velocity, if I take common, I left out with, you have uy by h plus u minus uy by h plus u. So therefore I end up with 1 minus y by h, minus uy by h. So here it will become plus, right? I think here people are confused. Let me substitute and show one more step here. That is, u will become, small u will become 1 by eta dp by dx y square by 2 plus C1y. C1 is this one, right? Plus C1y means minus 1 by 2 dp by dx hy minus u by h into y plus C2 is capital U. This is what we have. Now in these two terms I taken 1 by 2 eta. 1 by 2 eta dp by dx. If I take common, I get y square minus hy, correct? In these two terms I have taken u common, it will become 1 minus y by h, correct? So this is the expression for velocity. So how many assumptions we have employed? We have employed till here. No slip occurs between oil and the bearing surface. Let me write this velocity equation. I will end up with, now moving ahead, just now we have derived expression for velocity. Moving next, pick up the next assumption, that is oil is incompressible. So what do you mean by oil is incompressible? If oil is incompressible, then volume flow rate should remain constant, right? So next, if I take oil is incompressible, that is volume flow rate is constant. What is the formula for volume flow rate? Volume flow rate is velocity times the area. Velocity times the area. Let us consider u is the fluid velocity in x direction, v is the fluid velocity in y direction, and w is the fluid velocity in z direction. U, v and w, right? So therefore entry volume of fluid is velocity is u in x direction. In x direction, if I take, it is area will be dy dz. Let v be the velocity in y direction, area will be dx dz, and let w be the velocity of the fluid entering the element in z direction. W is the velocity, area will be dx dy. So this is the volume flow rate of fluid or lubricant entering the element in x direction, y direction, z direction. Velocity times area, velocity times area, velocity times area. What is the x direction area? This is dz dy. Dz dy is the area in x direction. What is the y direction area? Dx dz. Dx dz. What is the z direction area? This is dx and this is dy. Z direction area is dx dy. Z direction area is dx dy. U is the velocity in x direction, velocity in y direction, velocity in z direction. Leaving, there will be rate of change, right? So when it leaves, we have the rate of change, that is u plus dou u by dou x dx of dy dz. Entering must be equal to leaving, plus v plus dou v by dou y dy dx dz plus w plus dou w by dou z dz dx dy. Now if I take right hand side to left hand side and subtract, what I will get? I will end up with on simplification, this minus u dy dz cancels off, v dx dz minus v dx dz cancels off, w dx dy minus w dx dy cancels off. I left out with dou u by dou x dx dy dz minus dou v by dou y dx dy dz minus dou w by dou z dx dy dz. This must be equal to 0. I will take minus sign or throughout multiply by minus sign and take volume outside and send it to right hand side. I left out with dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. What do you call for this equation in fluid mechanics? Yes, you are correct. This is continuity equation of fluid mechanics, that is conservation of mass. Now move for the next assumption. Our next assumption is no flow in the direction perpendicular to motion. So what is the direction perpendicular to motion? That is in z direction, there is no flow. So therefore dw by dz must be equal to 0. So from our last assumption, that is now there is no flow in z direction, therefore dou w by dou z is 0. No flow in direction perpendicular to fluid motion, that is in z direction there is no flow. So therefore dou w by dou z is equal to 0. Hence I end up with the equation dou u by dou x is equal to minus dou v by dou y, minus dou v by dou y. Now what is the value of dou v? What is the value of dou v? That is, I can write it as dv is equal to minus dou u by dou x into dy. So this is what I will get. Right. Now I can integrate this equation. Now integrate this equation. If I integrate this equation, I will get Reynolds equation in 2 dimensions. Come, let us integrate this equation number. Let me take this equation as equation number 4 and continuity equation as equation number 3. Equation number 3. Let us integrate equation number 4 by substituting u. What is the value of u? Velocity at any point is nothing but this one, right? So put this u here and integrate over the length y varies from 0 to h. Let us do that. If I do that, that is, we had the equation dv is equal to minus dou by dou x of minus dou u by dou x dy, right? So this is what our equation 4 just now derived. Now let us substitute velocity equation and integrate this over the height h. Integrate it over the height h. So if integrate this, we have integral is from y is equal to 0 to h, dv is equal to minus dou by dou x of integral of u. U is what? 1 by 2 eta dp by dx y square minus hy plus maximum velocity times 1 minus y by h with reference to what? Dy, where y varies from 0 to h. Correct? Just I substitute for u and bring out the integral, because I should integrate over the entire length, that y varies from 0 to h. Now velocity v at h. What is the velocity v at h? We have only velocity in u. There is no velocity v for us. So therefore velocity v at y is equal to h minus velocity v at y is equal to 0. Both are 0, right? So let me substitute that. This must be equal to minus dou by dou x of, let me integrate this equation with reference to y. If I integrate this with reference to y, what I will get? 1 by 2 eta dp by dx, integral of y square is y cube by 3 minus h into y square by 2 plus capital U times dy is y minus integral of y is y square by 2h. So limit y varies from 0 to h. y varies from 0 to h. Velocity v at y is equal to h is 0. Velocity v at y is equal to 0 is 0. This is 0. 0 is equal to minus dou by dou x of 1 by 2 eta dp by dx. Let me substitute the limit. Upper limit is h. It will be h cube by 3 minus h square into h is h cube by 2. Lower limit is 0. 0 minus 0 is 0. 0 into anything is 0. Leave it. Plus maximum velocity is u. Upper limit is h minus h square by 2h. It is h by 2. Lower limit is 0. 0 minus 0 is 0. 0 into anything is 0. Leave it. So this is what I got. Now send this negative sign to left hand side. So this negative sign will get vanish. So if I write this, I end up with dou by dou x of 1 by 2 eta dp by dx. How much this will be? This will be 2 minus 3. 2 minus 3 will be minus 1. So that is minus h cube by 6. Minus h cube by 6 plus u of h by 2. This must be equal to 0. Now I can write this as, let me write, since I taken it as dv, let me write as normal derivative d d d d d d, because we are differentiate. So I end up with what? Let me take this to here, let me take this to here. If I do that, 6 2s are 12. So I will get 1 by 12 eta, correct, 6 2s are 12, eta is constant, 1 by 12 eta d by dx of dp by dx of minus h cube let me take this like this, plus let me took it here also. If I take here, I will get u is u max, that is constant. So therefore I will get maximum velocity by 2 dh by dx, which is equal to 0. So since I have negative sign, I can take this to one side and take this to another side. So if I do that, I will get d by dx of dp by dx of h cube. This is equal to 12 eta. If I send that side, it will get 12 eta u by 2 dh by dx, which is nothing but d by dx of dp by dx of h cube is equal to 6 eta times the maximum velocity u into dh by dx. So this is called Reynolds equation in 2 dimension. So this is called Reynolds equation in 2 dimension. So this is a derivation for Reynolds equation. So in today's lecture we have discussed hydrodynamic bearing, how the pressure development takes place in hydrodynamic bearing, what is the meaning of lightly loaded bearing, and Petrov's equation. I didn't derive here because I already derived it. I have given the link for that. Kindly click on the link given in the description to get access to the lecture on derivation of Petrov's equation. And later on we have discussed, after discussing the pressure development mechanism in a converging wedge, we have derived Reynolds equation in 2 dimension in detail based on the assumptions. That's all from this lecture. Thank you all.